Hello everyone. In this session, we are going to study the stability of stars. So when you discuss stability, we need to find equilibrium point at first. For example, if you consider a ball located on the top of a mountains, or if you place a ball in the bottom of the ball, in both cases, actually total net force is zero. So if we place the ball, red ball, on the top of the mountain or bottom of the ball, this ball doesn't move. So we call this point the equilibrium point. Then we'd like to discuss the stability. If the equilibrium point is a stable equilibrium point or unstable equilibrium point, we need to consider the perturbations from the equilibrium point. If the ball is moving a little bit away from the equilibrium point on the top of the mountains, this ball starts moving away from the equilibrium point. In this situation, the equilibrium point is an unstable equilibrium point. When the ball is moving away from the equilibrium point, when the ball is located at the bottom of a ball, then this ball is oscillating around the equilibrium point. So in this situation, we call it a stable equilibrium point. So we have two different types of the equilibrium point. In this session, we'd like to find out the conditions for the stabilities of the equilibrium state. First topic is the secular thermal stabilities. Second topic is the thermal stabilities. Third topic is the dynamical stabilities. Fourth topic is the dynamical instabilities. Fifth topic is the convections. So first topic is the secular thermal stabilities. So total energy of a star in the hydrostatic equilibrium is given by the internal energy of U plus gravitational potential energy of omega. And the virial theorem actually related P over rho integrate with respect to the m from the 0 to the capital M is the total mass of a star. It becomes a minus omega. This is the virial theorem. Then for the ideal gas with negligible radiation pressures, for ideal gas with non-negligible radiation pressures, we'd like to consider total energy of a star. So internal energy of the simple classical gas energy of simple classical gas and completely degenerate gas. I have explained U internal energy is expressed 3 over 2 P over rho. This is the case of the internal energy for simple classical gas and completely degenerate gas. So in the case of the internal energy of relativistic completely degenerate gas, and radiations. In this case, internal energy is expressed 3 times P over rho. So from this equation, you can find 3 times 0 to the m P over rho dm is expressed from this first equation. You can find 2 times m over 0 u sub gas. So in this case you can cite u gas dm plus 0 to the m. In this case radiation pressures u rad dm. So in this case you have a u sub rad. First term, this corresponds to the u sub gas, capital U sub gas. And second terms, this corresponds to the u sub radiation, internal energy of radiations. And then from the virial theorems, this is gonna be equal to the minus omega. So from these equations, we discovered 2u sub gas plus u sub radiations equal minus omega. So u gas, u sub gas is equal minus 1 over 2 omega plus u sub radiation. So we derived this relation. Internal energy of the gas is expressed the gravitational potential energy and the internal energy of radiations. So I have explained this case. In the case of the negligible radiation pressures, you can say the U rad is 0. Then we have this relation. Then total energy is a U plus omega. So when the ideal gas, so this is E equal U plus omega. Then you can substitute this here. Then it becomes 1 over 2 omegas. Or it becomes minus U. Okay, minus U. So it's internal energy of gas. In the case of the ideal gas with a non-negligible radiation pressures, total energy is omega U gas plus U rad. Then if you substitute this here, then it becomes 1 over 2 omega plus U sub rad. This is expressed minus U gas. In both cases, total energy is expressed by internal energy of gas. Then we'd like to consider the stabilities of a system, growth of perturbations. If we consider the nuclear reaction rate is larger than the luminosities, escaping energies from a star's L, but the generation of the energy is larger than the escaping energy of the luminosity. Then energy is increasing because energy production is larger than the rate of the emission of the radiations. So energy is increasing. So as I explained, energy is expressed minus U sub gas. So find the derivative. You have these relations. Energy is increasing. The left hand side is a positive quantity. So this is positive. Then U gas, du gas over dt have to be the negative quantities. So internal energy is decreasing. So this means the star is cooling down. Temperature is going to drop. And the d omega dt. So because U equal minus 1 over 2 omega. So this means omega is a negative sign. D omega dt has to be the positive quantities. So this means the star is going to expand. Actually the radius is increasing. So by the dropping the temperatures, nuclear energy production rate is decreasing. L sub nuc is equal to the L inside of the stars nuclear energy production rate is equal to the rate of the emission of radiations. So thermal equilibrium is restored. Then thermal instabilities. So now we consider pressure of the degenerate gas is insensitive to the temperatures. So we consider same situation. L sub nuc is larger than the luminosities. Then this is gonna be positive. And this is same answers. Then it's omega dt is the same. So star is going to expand. The star is going to expand. Expansion of the surface. du gas dt is a negative quantities, but this does not mean the temperature is going to drop, because U is expressed in the case of the degenerate gas is 1 over rho 3 over 2 8 pi over 15 mh cube p sub 0 cubes, and p sub 0 is 3 n sub e is the number density of electrons, 8 pi over 1 over 3 h. So U gas, in this case U gas is independent. Of temperatures. So U gas is going to decreasing, but this does not mean of the temperature is dropping. So L nuc is sensitive to the temperatures. L nuc does not decreasing. So keep L nuc is larger than the luminosities. So energy is increasing. So the star is keep expanding. So instead restorations of the thermal equilibriums are run away from the equilibrium ensues. So we call that thermonuclear runaways. This was proposed by the Lees in 1950s. Nuclear reaction ignite in the degenerate gas end up with the expansion of the surface of the stars and the explosion on the surface of the white dwarf. Okay, this is the end of this session.